we're going to talk about the concept of conditional probability and its basic properties. Assume that the probability of event B is positive, that is, strictly greater than 0. Then the probability of event A occurring given event B is called the conditional probability. Its notation and definition are shown in the second to last line. Intuitively, it represents the probability of event A occurring after event B has already occurred. In other words, using the probability of event B as the base reference in the denominator, we measure the probability that both events A and B occur simultaneously. We can think of the given event B as specifying a new sample space. On this basis, we wish to calculate the probability of that part of A contained within B, thereby determining the conditional probability P of A given B. Roll a pair of 6-sided dice and determine their sum. Let it be the event that the sum is 3, and let B be the event that the sum is either 3 or 5. Under the condition that event B is known to have occurred, calculate the conditional probability of A. There are 36 possible outcomes when rolling a pair of dice. Event A occurs in 2 cases, namely 1, 2, and 2, 1. Therefore, the probability of event A is P of A equals 2 over 36. Event B occurs in 6 cases, 1, 2, 2, 1, 1, 4, 4, 1, 2, 3, and 3, 2. Therefore, the probability of event B is P of B equals 6 over 36. According to the definition of conditional probability, we must compute the probability that events A and B occur simultaneously. It is easy to see that the simultaneous occurrence of A and B is simply event A itself, which gives the second equality in the last line of the equation. Based on the previous description, the calculation in the last line is straightforward to follow. Given any event B, we can define a set function as shown in the second line. We can prove that the set function defined via conditional probability remains a probability measure. The proof is as follows. We aim to prove that the set function conditioned on B satisfies the 3 axioms of a probability measure. First, the first condition that P of A given B is non-negative is straightforward to see. Since the probability of any event is non-negative, both the numerator and denominator in the conditional probability expression are non-negative. Second, we must prove that P of S given B equals 1. This calculation is shown on the last line, where the first equality follows from the definition of conditional probability and the second equality holds because event B is always contained in the sample space S, making S intersect B equals B, which completes the proof for the second condition. Next, we prove the third condition, which is countable additivity, sigma additivity. The calculation begins on the third line. The first equality on the third line follows from the definition of conditional probability, while the second equality uses distributive set operations, specifically that the intersection of a union equals the union of the intersections. On the fourth line, the numerator in the first equality applies the countable additivity of the probability measure, and the second equality is straightforward to see. Applying the definition of conditional probability once more yields the expression on the second to last line, which completes the proof. We can rewrite the definition of conditional probability to obtain the mathematical expressions on the third to last line and the final line. This approach of using conditional probability to compute the probability of events A and B occurring simultaneously is known as the multiplication rule. Intuitively, the probability of both events A and B occurring can be conceptualized as the probability of event A occurring first, multiplied by the conditional probability of event B occurring given that A has occurred, as shown on the third to last line. Similarly, the probability of both events A and B occurring can also be thought of as the probability of event B occurring first, multiplied by the conditional probability of event A occurring given that B has occurred, as shown on the final line. A bowl contains 7 blue chips and 3 red chips. 2 chips are drawn at random sequentially without replacement. We wish to calculate the probability that the first chip drawn is red, event A, and the second chip drawn is blue, event B. Since there are 10 chips in total, the probability of event A, drawing a red chip, is P of A equals 3 over 10. After event A has occurred, only 9 chips remain. Therefore, given event A, the conditional probability of event B, drawing a blue chip, is P of B given A, equals 7 over 9, as shown on the second line. Therefore, by the multiplication rule, the calculation for the probability that the first chip is red, event A, and the second chip is blue, event B, is presented on the final line. Next, we consider the multiplication rule for the simultaneous occurrence of 3 events. The first equality on the second line treats the joint occurrence of 3 events as that of 2 events, regarding A intersect B as a single event. Therefore, we can apply the 2-event multiplication rule, as shown by the second equality. Next, applying the 2-event multiplication rule again to the probability of A intersect B yields the mathematical expression on the fourth line. Combining these two expressions gives the multiplication rule for 3 events occurring simultaneously, as shown on the final line. Intuitively, this means that the probability of events A, B, and C occurring together equals the probability of event A occurring first, times the conditional probability of event B occurring given A, times the conditional probability of event C occurring given that both A and B have occurred. We can also express this in different forms. As explained on the second line, the probability of events A, B, and C occurring simultaneously equals the probability of event B occurring first, multiplied by the conditional probability of event A occurring given B, and then multiplied by the conditional probability of event C occurring given that both A and B have occurred. Similarly, the final line illustrates that the probability of events A, B, and C occurring simultaneously equals the probability of event C occurring first, multiplied by the conditional probability of event A occurring given C, and then multiplied by the conditional probability of event B occurring given that both A and C have occurred. Several other variations can be obtained in the same manner. An elementary school student has 5 blue marbles and 4 white marbles in his left pocket, and 4 blue marbles and 5 white marbles in his right pocket. If he randomly draws a marble from his left pocket and places it into his right pocket, what is the probability that a marble subsequently drawn from his right pocket is blue? In terms of notation, let BL, BR, and WL denote drawing a blue marble from the left pocket, drawing a blue marble from the right pocket, and drawing a white marble from the left pocket, respectively. We will calculate the probability of event BR drawing a blue marble from the right pocket can occur in 2 ways. Either a blue marble is drawn first from the left pocket, represented by BL intersect BR, or a white marble is drawn first from the left pocket, represented by WL intersect BR. Since these 2 respective intersection events are mutually exclusive, the expression on the second line follows from the third axiom of probability measures. Applying the multiplication rule then yields the calculation on the third line. The probability of event BL is straightforward to see. That is, drawing a blue marble from the left pocket gives a probability of 5 over 9. Under the condition BL, the right pocket now contains 5 blue and 5 white marbles, making the conditional probability P of BR given BL equals 5 over 10. This provides the calculation for the first term using the multiplication rule on the second to last line. The second term using the multiplication rule can be derived in the same manner, completing the calculation. This theorem states the multiplication rule for computing the simultaneous occurrence of and events using conditional probability. Its proof can be completed by mathematical induction and the multiplication rule for the simultaneous occurrence of two events.